Okay, I'm back. This is problem 3 from project 2 for the summer 2014 Tempo ePortfolio project. Alright. A heat pump receives heat from a lake that has an average winter time temperature of 6 degrees C and supplies heat into a house having an average temperature of 27 degrees C. Part A. If the house loses heat to the atmosphere at the rate of 64,000 kilojoules per hour, determine the minimum power supplied to the heat pump in kilowatts. Part B. A heat exchanger is used to transfer the energy from the lake water to the heat pump. If the lake water temperature decreases by 5 degrees Celsius as it flows through the lake water to heat pump heat exchanger, determine the minimum mass flow rate of the lake water in kilograms per second. Neglect the effect of the lake water pump. Alright, so part A first. We're looking to find the minimum power needed to run the heat pump in kilowatts. So we're going to start off with the COP for heat pump equation, which is equal to 1 over 1 minus QL over QH, which we're going to assume it's reversible, which is the equivalent of 1 minus TL over TH. So we're given our TL, which is the heat coming from the lake, is 6 degrees C, which is equal to 279 K. Remember, for this equation we have to use absolute temperatures. So TH, which is given in the problem as 27 degrees C, which is equal to 300 K. So now we can find our COP, substituting those values in. So our COP of our heat pump is, let me find it on my paper, 14.29. Alright, now that we know our COP, and that's our COP max, we know that our COP is equal to Q dot H over W dot N for heat pumps. So now we just rearrange to solve for W dot N. So our Q dot H, we're given 64,000 kilojoules per hour. And then keep in mind that that's 1 hour per 3,600 seconds. And this whole thing is divided by our COP of 14.29, which we just found previously, to equal our W dot N minimum of 1.24 kilowatts. Okay, so now we'll go to the next slide for part B, I guess, in which we're wanting to find the mass flow rate of the lake water through the lake water heat exchanger. So before I do, we're going to go to our little picture here, and we're going to define our CV as this around our heat exchanger. So keep that in mind as we're setting up our equations on the next slide. Alright, so for part B, we're assuming it's a steady system. I mean, most heat pumps operate steadily. So En equals E out, which we can write our big equation of Qn plus Wn plus m dot H1 equals Q out plus work out plus m dot H2 out. We know that m dot 1 is equal to m dot 2 since it's flowing one way. There's one way in and one way out of the heat exchanger. We know that there is no work being done, no moving parts. It's a heat exchanger device. It's not a piston or anything like that. We also know there's no heat coming in. So rearranging a little bit here and knowing that Q out is equal to Q L, we can rearrange to solve for our mass flow rate. So m dot H1 minus H2 equals Q dot L. Okay? And then m dot equals Q dot L over H1 minus H2. Alright, now we have our equation set up. Now I have to figure out what we need to find out to solve it. So QL, do we know QL? We don't know QL right now. However, we do know this formula, QH minus QL equals work net. So the previous problem, we just found our work net, which was 1.24. And we also found our QH, which we calculated a little bit. That was the 64,000 divided by 3,600 term. So now rearranging a little bit here, we can solve for QL, which is simply QH minus W net. So QL is going to be 64,000 divided by 3,600 minus 1.24, which gets us QL 16.53 kilowatts. Okay, so now we know QL. Now what about H1 minus H2? We don't know any information about the different states coming in. So similar to the previous problem, and this is water again, we know that delta H, which is simply H1 minus H2, is equal to Cp delta T, or our specific heat times change in temperature. Given in the problem statement, we know that delta T is 5 degrees C, and looking at table A3 as before, we get a value of 4.18 kilojoules per kilogram Kelvin. Multiply those out. We get a delta H of 20.9. So now we have this part. So now we can set up to solve. Our 16.53 over 20.9, and we arrive at a mass flow rate of lake water to be 0.791 kilograms per second.